So we finished yesterday talking about projection. So let's warm up with that and see a little bit of examples. I don't think we did too many examples of things that we can do with projections and this concept of orthogonality. And then the main topic for today is going to be linear independence. Maybe we'll get to bases. So this is mostly out of section 4.10 of the book. And we have 2 days on this. So if you're checking the schedule, linear independence and bases, we're going to spend 2 days on it. It's a big topic, something we want to give it the time for. So we will introduce the concept of linear independence. And then if we have time at the end, start to talk about what a basis for a vector space is. And if we don't get to it, we'll just pick right up from there when we start tomorrow's lecture. So let's do some projection warm-up. And we just remember that our projection onto U of V, so just remember it's projection of V onto U. What we want to do is to compute the inner product scale it by 1 over the length of U, and then find that vector, or then scale the vector in the direction of U, the unit vector, so U over norm U, in the direction of U. So we end up with 2 factors of norm U in the denominator. And of course, this notation just means the inner product is a dot product. I might start using that a little bit more, since writing these dots if you're writing them quickly as you're working out problems, it can be confused with a scalar multiplication. And they're both very similar, scalar multiplication and this dot product, in terms of how they behave. But sometimes you do want to be careful, and just to make sure of the objects you're working with, whether they're scalars or vectors, especially in a course like this. So let's do a couple of examples. And primarily, projections and dot products have a big use in this geometric concept of orthogonality. So we saw yesterday, of course, this is the projection of V in the direction of U. And if we wanted to find V a perpendicular vector, let's actually write down that formula as well. So we notice that any vector V we can write down as a parallel component in the direction of U plus a perpendicular component. And of course, our parallel component was just our projection. And then how did we find the perpendicular component? We just took the original vector V and subtracted off the parallel component. And that will give us the perpendicular component. And what we showed was that if we actually do this, then this vector, if we do all our computations correctly, this perpendicular component we compute is in fact perpendicular. At least we showed this for one example, that when I take a dot product, maybe we should write that again too, to orthogonal, means our dot product is 0. V dot U or U dot V is 0. And so we checked that for this perpendicular component to make sure it matched with our intuition and our geometry. So this comes up in distance. So if we give you a problem or an example where, let's say we have a point P is 135 in R3, and distance L is a line through 0, 4, minus 2 in the direction of our directional vector 2, 1, 2 we want to find the shortest distance from a point, from the point to the line. So hopefully somewhere in your geometry class or in calculus, you learned that the shortest distance between a point and a line, or a point and a plane, is a line perpendicular to the given line or plane, respectively. Right, if we have a line, and of course now we're in 3 dimensions, so this line could be angled and skewed and rotated in any way, shape, or form. And I could have a point here. The direction we want to travel straight to the line, but wherever we hit the line, we want the angle now of intersection between those 2 points, or between those 2 lines, to be 90 degrees. And you can see this just by example. If we were to draw any other lines, we could see that the lines we travel from this point to the given line are going to be longer. So the distance we would walk from this point to get onto this line would be longer if we don't follow a perpendicular. Likewise for planes. If we have a point somewhere outside the plane, we want to walk in such a way so that when we hit the plane, the direction we walked at is perpendicular to that plane. So let's go ahead and write down our information. Since we're using some extra pages here, we had P was 1, 3, 5. Our line consisted of our points 0, 4, minus 2, and with a directional vector of, I'll put that in the column now, 2, 1, 2. So we can go ahead and parameterize our line. Let's go ahead and write it as a function L of t. And we can define our line actually now as a vector valued function. If you don't put the arrow over it, don't worry about it. L as a function of t is going to be a function that takes values in R3. And so it's simply going to be our starting point, now written as a position vector, plus our directional vector times t. And then if we wanted to write out our system of parametric equations for our coordinate variables, we will simply have x is 2t, y is 4 plus t, and then z is minus 2 plus 2t. And so what we need now is a notion of when am I going to hit this line? We're walking from this point, and then we're going to end up on a line whose points, whose coordinates are parameterized by these equations. So we walk from P to some point, x, y, and z. We know the point is on the line. We don't know specifically the parameter t that we're going to hit at, but we at least know the direction we're walking, or at least we can now come up with an expression for our direction, right? The point P is not a vector. It is just a point, though you could consider it as a position vector in three-dimensional space. The direction we are walking at so of course I'm using this notion of us walking from P towards this line. You could also describe it as our directional vector to the point on the line. Let's call the point on the line Q. So we have our line, we have our point. I know I'm going to walk somewhere and then in a straight line, and then we're going to walk from P and we're going to hit Q. So no matter what point we land at Q, of course, Q is going to be able to be given coordinates following the functions we found. Then the direction vector is simply given by the difference between those points. So let's call that our U. So our U is going to be P minus Q. And actually, let's do this. Let's do it Q minus P. Ending value minus our starting value. So that way it'll point from P in the direction of our line towards the line. And so what are we going to have? That's just going to be a vector of our x coordinate minus our x coordinate for our P. And then likewise in the other coordinates. And so since we have actual values for those, let's go ahead and plug those in. We've got 2t minus our P1 is 1. For our y, we've got 4 plus t minus our P2 is 3. And then our z, minus 2 plus 2t minus 5. And so now this I have written in vector form. This is a vector. And this vector, u, is going to change depending on t. So t is going to correspond to wherever we land, wherever q is. So the direction we're going to walk is going to change depending on wherever we land. And so our goal is what we've done, is what we've rephrased, is we really want to find the correct t, the correct parameter that corresponds to the perpendicular. In other words, what value of t will make this directional vector perpendicular to the directional vector of our given line. So we want the dot product to be 0. And so now we can compute that. Let's go ahead and write it as v dot u. So our v we can write as v transpose. So 212 times our 2t minus 1. 4t minus 3 is going to be 1. 4 plus t minus 3. 1 plus t is what it will simplify to. And then, of course, minus 2t plus minus 2 plus 2t minus 5 minus 7 plus 2t. So the dot product, of course, we can write as a product of a row vector and a column vector. And what's that going to give us? That'll give us 2 times this guy. Will give us 4t minus 2 plus 1 plus t plus minus 14 plus 4t. We need that to be 0. Let's see if we've got enough space here to solve this. So it's just a linear equation. How many factors of t do we have? We've got 4t, t, and 4t. So we've got 9t. And then our constant minus 2 plus 1 is minus 1. Minus 14 gives us minus 15. And so our t, 15 over 9, is 5/3. So what does this tell us? So let's go back and summarize everything. We're starting at this point P, 1, 3, 5. We know for any point on the line, we would hit a point with coordinates x, y, or z in z. And we found out the point we need to hit in order to have a perpendicular direction of travel is going to have a t value of 5/3. In other words, we can find our q now. Our q is going to be obtained by solving our parametric equations. So x of 5/3, y of 5/3, z of 5/3. So our x coordinate was 2t. Our y coordinate was 4 plus t. And our z coordinate is minus 2 plus 2t. So our q is 10/3, 17/3, and let's see, we've got 10/3 minus 6 is going to give us 4/3. So if we found our P, or we're given our P, we found our Q, and we know that this Q lies on our line, and this is where we are going to land to hit our perpendicular. The question of the problem, though, asks, what is the shortest distance? We actually have to find the distance now between P and Q. So difference of the x coordinates, so that's going to give us 10/3 minus 1, 7/3 squared. 17/3 minus 3 is going to give us 8/3 squared. 4/3 minus 5 is going to be 4 minus 15, so negative 11/3 squared. Add those all up and then take a square root to find our distance. So unfortunately, these numbers don't look to be the nicest. So 49 over 9 plus 64 over 9 plus 121 over 9. And what are we going to get? Let's see, 64 and 121 is 185. and 49 is going to give us 234. So that's going to be our distance. Will that simplify at all? Let's see. What's 234 factor? 234, so real quick factorization. 2 and 167, and then 167. God knows how that factors. So let's just keep it as it is. 167 might even be prime. So about the simplest we can get that number, square root of 234 over 3. Okay. I don't want to work through this problem, but maybe we will talk through it. What about if we had a plane that is defined by some initial vector plus our two directional vectors? Sorry, let's write it, let's write it s times u plus t times v. And the point P. If we wanted to find the shortest distance, how do we find that? Could we generalize the previous methods? We could. So what we would want to do is, for one, we're going to come up with a parameterization of our coordinates, our x, y, and z, if this were in, say, 3 dimensions, with now 2 parameters of s and t. And so our goal would be to find the s and t, which would give us the point on the plane that is perpendicular to the line connecting it to P. So you'd have to do that, but in order to find S and T, you would need at least 2 equations. So think about that and think about how you would get that second equation. So of course, we would want the directional vector from P to Q to be perpendicular to the plane. And so maybe you should think about, well, if something is perpendicular to the plane, it'll be perpendicular to both U and V. So we'd have two equations to solve, two equations from perpendicular orthogonality. I don't know if perpendicularity is a word, but orthogonality is one. So 2 orthogonality equations from the dot product from the vector from P to Q. And you would take the dot product with both U and then another dot product with V and set both of those equal to 0 to try to determine your parameters. Maybe if we've got time, we'll see an example like that. But for now, let's go ahead and move on and talk about linear independence. So just some definitions. Suppose we'll use capital letters, capital U, capital W are sets of vectors. in Rn, and all vectors in U are also in W. In other words, U is contained in W. Then we call U a subset of W. And then we denote that by kind of like that sideways E, like that element, but just like a sideways U, I guess. So U is contained in W. U is a subset of W, is another way we could say that. So some other definitions. So we let capital U, and let's say we have a subset of vectors in Rn. Then we define the span of U, or sometimes we write it the span of that set or collection of vectors to be the set of all linear combinations of vectors in U. In other words, we can define the span of U to be the set. What is a linear combination? Remember, we are just taking scalars, multiplying them by the corresponding vectors. So forgive me, I haven't been writing the vector arrow above the vectors. So we take scalars times the vectors, and then we add all those up. So in some sense, we've been doing this a little bit with planes. We have our planes and a plane, not an affine plane. So a plane that passes through the origin, we've defined by two directional vectors and then scaling those directional vectors with two different constants. So we could describe a plane as simply the linear combination, or the set of all linear combinations of two directional vectors. So let's take a look at some examples. So let U equal to 1, 1, 0 and V equal to 3, 2, 1. Which are in the span of U and V. And so I've got a few vectors we want to check. Let's say A, we've got W is equal to 4, 5, minus 1. And B, we've got X is 2, 3, 0. So our first step is to write out a generic equation. We want to see if W is in the span. We want to know, can we write W as some scalar multiple of U plus some other scalar multiple of V? So you can use S and T for your scalars, T1, T2, however you want to denote those. So let's go ahead and write out what this means. We've got T1 times 110 plus T2 times 321. And this process should now look fairly familiar. And let's go ahead and write out our W was 4, 5, minus 1. And so what do we have? We have these equations in each coordinate. We're going to have T1 plus 3T2 is equal to 4 for the top equation. We'll have T1 plus 2T2 is equal to 5. And then we're going to have T2 is equal to minus 1 for the bottom row. So we are doing the exact same thing we've done in the past couple of days with looking at planes. So another way of looking at this is asking, is W on the plane spanned by U and V? So we can use this word span now, especially in terms of planes and subspaces, as we will see once we get in the higher dimensions. So is W in the plane spanned by these two vectors? Is it in the space spanned by those two vectors? And so let's check. One of our equations is nicely solved for us. We know that T2 has to be minus 1. And so by the second equation, or I guess we can label them, let's call it 1, 2, and 3. Equation 3 was solved for us. Equation 2 tells us that T2 has to be 7. And again, we need a consistent system, so we would check 7 plus 3 times T2, which is minus 1, equals 4. So 7 minus 3 equals 4 works. So we have a consistent system, and we can say, yes, W is an element of the span of U and V, since W is equal to 7U minus V. To check our X variable, let's go ahead and use S and T for our constants in this solution. Sorry, that's a V. I keep making that mistake. And our X was 230. U was 110. And V was 321. So once again, we have a system of equations where we have S plus 3t is equal to 2, S plus 2t is equal to 3, and then the bottom equation says t is equal to 0. So of course, bottom equation being solved is easy enough. That will tell us that S should be 3 from the second equation. And then we want to check to make sure we are consistent with our first equation. And we are not. So our conclusion here is that this x vector is not in the span. So we just take that element and then draw a line through it to say that it is not in the span of u and v, since there are no constants such that x is a linear combination of u and v.
I have a quick question.
Yeah.
So, why in A was the equation set up with T1 and T2 as constants, whereas in B it was set up with S and T?
Just by choice, whatever ones you want to choose. So whatever letters you want to use for your constants. In this equation, since we only had 2, S and T are kind of nicer to use, but T1 and T2, not wrong.
Okay, so like that, it's the same operation. All right.
Yeah, same I mean, the math behind each one was the same. Whatever variables you want to use for your constants, feel free. Usually I've been using S and T for constants. Some books, they use the Greek letter lambda for your scalar constants. And then if you want to use, S and T, or if you want to use S1, S2, S3, if we have 3 vectors, you can use that as well. Okay, so let's do an example. And let's say we've got U1 is 0, 1, 2. U2 is -2, 3, 2. And U3 is 1, -2, 0. Show that U1 plus U2 plus 2U3 gives us the 0 vector. So again, we're just taking a linear combination of U1, U2, and U3. And what are we going to get? So let's go ahead and write it out. 0, 1, 2 plus -2, 3, 2 plus 2 times 1 -2, 0. Our top coordinate, we're going to have 0, -2 plus 2 gives us 0. Bottom coordinate, 1 plus 3 gives us 4, minus 4 also gives us 0. And then it looks like I missed a minus sign somewhere. Yeah, this guy should have been negative. -2 plus 2 gives us 0. So this brings up an interesting concept. Namely, when can we get 0 from a linear combination? We can see that these 3 vectors, the linear combination we took is what we call non-trivial, meaning the coefficients are non-zero. So this is our definition of linear independence. So let's formalize this. So, definition. A set of vectors u1 up to uk are called linearly independent if any vector in the set cannot be written as a linear combination of the others. This is the idea. In other words, if I pick out one of these vectors, u sub I, it's saying that u sub I is not going to be in the span. Let's actually write it as not in the span of all the other ones. So u1 up to ui minus 1, ui plus 1, up to uk. Right? So the span is the set of all linear combinations. And so if we take one of the vectors out of the set and then look at the span of the remaining vectors, then the span of those remaining vectors will never hit the vector we left out. The vector we left out is not in the span. So kind of three definitions here are called linearly independent if. So one, we can think about it in terms of writing it as a linear combination. We can come up with an equivalent phrasing in terms of the span, or a third equivalent definition that if we take a linear combination of the vectors and get 0, then the only time this can occur, so if the linear combination is equal to 0, then we must have all of the constants equal to 0. In other words, so this only occurs when all of the ti, t1 equals t2 equals all of those equals 0. So there's going to be one more way we can phrase this. And we will take a look at matrices and how we can generalize this. Let's do an example first. So everyone caught up with writing everything? So our example check if the set of vectors are linearly independent. So I'm going to abbreviate linearly independent by lin_ind, so we don't have to write that out every time. And then our set of vectors is 1, 2, 3, 0, 2, 1, 0, 1, 0, 1, 1, 2, and 3, 2, 2, minus 1. So what we want to do, we can label them if we want. Let's call it U1, U2, U3, and U4. And this is going to be a case where for the scalars, I'm just going to use T1, T2, T3, and T4. We want to check for solutions to our equation T1 U1 plus T2 U2 plus T3 U3 plus T4 U4 equals 0. So this is using this last definition. We're going to look for solutions for whenever a linear combination of these vectors equals to 0. And if we find non-trivial solutions, so when I say trivial solution, this is what I mean. All the TIs are 0. So of course, if I plug in 0 for all of the T's, we'll get a valid equation. It'll work. So what we want to see is, can we have other values of these TIs and satisfy this equation? Okay, so once again, we're going to get a system of linear equations. So if everyone's got that down on their notes, let's go ahead and rewrite this now out with all of these vectors, starting on a new page here. And let's see how this math works out. So we've got T1 times 1, 2, 3, 0 plus T2 times 2, 1, 0, 1, T3 times 0, 1, 1, 2 plus T4 times 3, 2, 2 minus 1 equals 0. So kind of similar to these problems we've been doing in planes. We've just got a little bit of a different equation where we've got what would be called maybe a homogeneous equation, since we are setting it equal to 0. And let's take a look at what our system of equations looks like. So we've got T1 plus T2, 2T2, plus 0T3, let's keep that as a placeholder, plus 3T4 equals 0. 2T1 plus T2 plus T3 plus 2T4 equals 0. 3t1, 0t2, t3 plus 2t4, and then our last one, 0t1, 1t2, 2t3, and then a minus 1t4 equals 0. So this is the system of equations we get. And if only we had some nice, easier methods for solving systems of linear equations. Wait a minute, turns out we do, right? We have worked the first week and coming up with some row reduction methods, as well as possibly some LU factorization methods towards solving a system of linear equations. We also found methods of rewriting systems of linear equation in terms of matrices, in terms of either augmented or coefficient matrices. So how does that go? We can rewrite this matrix, or rewrite the system of equations as a matrix 1, 2, 3, 0, 2, 2, 1, 0, 1, 0, 1, 1, 2, and 3, 2, 2, minus 1, times a vector of scalars So check that. What's going to happen if we perform this matrix multiplication for this matrix acting on this vector of variables that we've created? Right, if I do the top row times the first column, it'll give us 1t1 plus 2t2 plus 0t3 plus 3t4 equals 0. It gives us the first row. Likewise, check the second one. 2t1 plus t2 plus t3 plus 2t4 equals 0 will give us the second equation. So this is how our coefficient matrix acts on our vector of variables. And now let's take a closer look. What do you guys notice about this matrix? What are special about the columns of the matrix? See if we can put this on screen here. Not easy. If we look at the set of original vectors and we look at this matrix, what is special about the columns? Those columns are exactly the set of vectors we started with. So namely, this is a matrix formed by using the vectors, and let's say using the set of vectors as columns. So this actually kind of builds a little bit of geometry involved in this notation. Matrices, if you have to take higher linear algebra courses and higher level math classes, Matrices are fantastic objects. There's many different ways to interpret what a matrix actually is and what it represents geometrically. In some sense, in this case, we can kind of interpret this matrix in some sense as defining or encoding the information of the span of the set of vectors defined by the columns. So it encodes that space within the matrix. And so how can we decode that information to determine, well, what exactly is the span of these vectors, of the column vectors? Is it actually a four-dimensional space, or maybe there's some redundancies in there? Maybe if these vectors aren't linearly independent, then that means one of these vectors is already in the span of the other ones. Meaning the span of this set of four vectors can be obtained equivalently with a span of only three of the vectors. So maybe we'll try to clarify that after that this example. And so our question is tying into that is going to become, well, how can we determine that information by this matrix and this matrix of row operations or possibly LU factorization, these techniques that we've developed for solving such a system. So all of that information we're trying to deduce by setting up the system of linear equations. And again, all of that is encoded now in our matrix equation of determining whether or not these vectors are linearly independent. And so how do we do that? Well, we want to solve for all of our variables, our T1, T2, T3, and T4. What's the easiest way to do that? Well, easiest, debatable. We could come up with an LU factorization. We could come up with an inverse of this guy if we wanted to, or we could simply try to perform row operations to try to see if we can come up with a non-trivial solution. So let's go ahead and stick with row operations. Let's go back to our tried and true methods. And so to solve that system of linear equations, we want to, it's going to be a lot of writing. So let's write it all out. 1, 2, 0, 3. And we are solving the homogeneous system of equations. So we've got 0, 0, 0, 0 as our extra column on the right. 2, 1, 1, 2, 3, 0, 1, 2, and 0, 1, 2, minus 1 for that last row. So let's see. Row 4 looks pretty good with a 0 there. I like row 3, pretty good with a 0 there as well. We will ultimately want both of those to be 0. And then we maybe want to finagle row 1 and 2. Appreciate your guys' work on the exam for this. A lot of you guys, I mean, it was a pain to check, but I think most people notated it very well, especially if you did multiple steps in one operation. So I was able to follow it and give you guys most of the points. Sometimes there was an algebra mistake, which was, maybe 1 point off. But other than that, like if you make one mistake in the beginning and then the rest of your work follows, I didn't take off extra points, down the line. And so thank you for helping me in notating your work so that I could actually follow your follow-up work, even if there was an early mistake, and make sure that you didn't make any more mistakes. And so usually that was only just a point off. Okay, so let's do 1, 2, 0, 3. We like that 1 in the first column, in the first row. And so let's do -2 row 1. And we're going to add that to row 2 and of course replace row 2. So that'll give us a 0 here. We will have -2, so -4 plus 1, -3. 0 and 1 stays 0. -6 plus 2 will give us -4, and then 0 still over here. Let's go ahead and get rid of that one too. So -3 row 1 plus row 3. Of course, doing this, you do got to be careful with notating in the order of things. So since we're using only row 1 to affect the other rows, the order of operations doesn't matter, right? Between doing this one first or doing this one first. And I think most people were good about that. I would say be careful. Like if we modify row 2 by adding a copy of row 1 and then use row 2 to affect row 3, careful with stuff like that, because sometimes it can be hard to follow as to whether you're using the modified row 2 to then affect row 3 or the unmodified one. So if you have to, draw an extra matrix. So what are we going to get here? 0 in the first coordinate, -6 there. And this coordinate stays the same. And then we've got -9 plus 2 gives us a -7. 0 still here in the end. And then this last row, let's just leave the same. 0, 1, 2, -1. And 0 there. So we want to be careful here because I actually want to move this row up to here, right? It's nice to have that 1. But it's going to correspond, right? This is our T1, this is our T2, this is our T3, and our T4. If you switch rows, it's kind of like switching the orders of the variables. So this is going to be something we actually want to keep track of. We will still find whether or not there's a degenerate or a non-trivial solution, but the actual values of that solution that correspond to the labels of the variables we chose, if we want to keep track of it, maybe we want to label the rows corresponding to that variable. So if we switch the rows, so right, if we have 1, 2, 0, 3, and now 0, 1, 2, -1, and then let's see, what do we want next? I don't think these two are going to matter much. So 0, -3, 1, -4, and then 0, -6, 1, -7. We can keep those in the same order. And then just to label our rows, this was T1, and now we moved T4 up to here. Sorry, little off screen there. Okay, so we want to proceed. We've got 1, 2, 0, 3, 0. We've got 0, 1, 2, -1. And now we want to remove the constants in the second column below our 1. So we are going to do 3 row 2 plus row 3. So we'll, of course, get a 0 there, a 0 there, and then 3 row 2 gives us 6 plus 1, so 7 there. And then -3, -4 gives us -7. Well, these two zeros, sorry, let's write out the constant. It'll be -6 row 2 plus row 4. Sorry, and I'm off screen. Let me know if I get off screen and you guys can't watch. So we want -6 times row 2 plus row 4. And then let's see, so we got our two zeros, and then row 2, we've got now -6, so that's -12 plus 1 gives us -11. Sorry, we don't need a minus there, do I? We've got a minus in that 6 already, so we want +6 row 2 plus that. So that'll give us 13. For that guy. So 6 and -1 give us -6, and 7 gives us -13 and 0. T1, T4, T2, and T3 were our order of our variables. Okay, and so now we want to finish this guy off. And it is a horrible pain, as most of these are. Looks like we can factor out a factor of 7 from T2 and a factor of 13 from T3, so maybe not too terrible. Oh, sorry. Just factor out the 7. So times 1/7, we'll have a 1 there, times 1/13 will give us a 1 in that row as well. Sorry, my brain's wandering a little bit. I'm actually trying to wonder if switching these mattered. It might not have. Let's think through it once we finish going through this process. Because in some sense, our T1 actually corresponds to this column because we had T1 times this column, T2 times this column. So I actually don't think switching the rows, I don't think we actually need this. I was flipping my row operations and column operations. So we'll explain that at the end. The key thing right now is finishing our row operations, and we'll see how and why this works out. Okay, so our third row is actually pretty good since we have a positive 1 here now. And then we just want to finish our row echelon form by adding minus row 3 plus row 4 now. So 0, 0. And what do we end up getting? So the row 3 and row 4 actually were the same. Sorry, off the screen again. So what happens if we get a row of zeros? Row of zeros is going to be not linearly independent. When we get a row of zeros. So let's see why. Let's go back and correct this. Sorry, I was thinking about our variables T1. This isn't right. You got to be careful with the column operations, but we don't do column operations necessarily in this class. I think I mentioned earlier that you can do row operations and column operations when you're finding these reduced row echelon forms and whatnot. But the correct way is that this is our T1 variable. This is our T2 variable. This was our T3 variable, right? We had T1 times this column, T2 times our second column. And then our T4 was corresponding to that column. And so when we are solving for our T4, essentially what this means, what we found, is, well, there's no equation for T4. So in other words, we can essentially find the span of all of those three vectors with just T1, T2, and T3. Let's go through this and put this in reduced row echelon form, or at least try to get as close as we can and see what happens with that and maybe clarify our solutions a little bit more. So let's go ahead and get rid of that 2. So we're going to have a 1, a 0, a 0. And what did we want to do? We wanted to do row 1 minus row 2 and replace it into row 1. So we got a negative 2, row 2. So negative 2 plus 2 gives us that 0. Negative 4 here. And then we will have 1, positive 1, or excuse me, positive 2 plus 3 gives us 5 in that fourth column. And then let's see, we'll keep our 2, our minus 1, our 1, minus 1, and zeros in the bottom row. These problems, they take up so much space. Let's keep writing. So now what do we want to do? I guess we should have started at the bottom, shouldn't we? And work our way up. I'm working in these opposite order. What's our row 2? So we want to take minus 2, row 3, and then add it to row 2. So we've got 0, 1, and then 0 here. Minus 2 will give us positive 2. Minus 1 gives us positive 1 there. And then we've got 0, 0, 1, minus 1. Unfortunately, we can't get rid of that 1 because our T4 variable isn't needed. And then now we can get rid of the 4 here. So we will do 4 row 3 plus row 1. So we'll have 1, 0, 0, and then row 3 we've got 4, which will give us negative 4, and then a 1 there. We've got 0, 1, 0, 1, 0, 0, 1, minus 1, and 0, 0, 0, 0, 0. All right. Bunch of row operations coming back. You could, again, try to solve that by finding the inverse, which we'll talk about a little more in a second, or the LU factorization might have been a little quicker. But what is this telling us? This is saying that the system of equations that we originally started with can be reduced down to this system of equations. In other words, the system of equations we now have is going to be T1 plus T4 is equal to 0. T2 plus T4 is equal to 0. And then T3 minus T4 is equal to 0. And now another way of writing it. T1 is minus T4. T2 is minus T4. and then T3 is equal to T4. So our T4 becomes, in some sense, a free variable. So we have a choice of T4. And if we change the order, if we actually did some column operations, we could choose either T1 or T2 as the free variable, or T3, any of the variables. But we at least have 1 degree of freedom. So let's pick a non-trivial solution. So non-zero. If we choose T4 equal to 1, this is going to say T1 equals -1, T2 equals -1, T3 equals 1, and we chose T4 to be equal to 1. And now we can check that -1 times our vector minus U2 plus U3 plus U4, should we get 0, and let's go ahead and pull up our notes. We've been working with a lot of pages here. So our original vectors U1, U2, this says that minus 1, 2, 3, 0 minus 2, 1, 0, 1 plus 0, 1, 1, 2 plus 3, 2, 2, 1. Sorry, 3, 2, 2, negative 1. And we are checking if this gives us the 0 vector. And what do we get? -1, -1, -2, plus 3 in that first column, first row. Of course, that's going to give us 0. We're going to have -2, -1, plus 1, plus 2 gives us 0. Third row, 3 plus 0 plus 1 plus 2 also gives us 0. And then in the last row, 0 minus 1 plus 2 minus 1 gives us 0. So our solution is no, our set of vectors are not linearly independent. So again, just lin-ind. You guys can abbreviate linearly independent as lin-ind as well on your homeworks or on the exams. Another way of phrasing this is you could say they are linearly dependent. So if they're not independent, they are dependent. And of course, if you want to abbreviate that, lin-dep or something like that, it's pretty clear what that means. Any questions on that? Okay, so that was quite a lot of computations there. These problems, man, they do just take some time. I don't think I'll ever put anything more than a 3x3 on the quiz or exams, unless there's like shortcuts. Like the one we just saw, there was a 4x4 using row operations, but it was only like 4 row operations away from the identity. So it was not many. It shouldn't have taken a lot of computations, a lot of row operations to simplify. Okay, so we only have about 5 minutes. Unfortunately, I wish we could kind of take a break and then come back, but we don't really have time. So maybe we'll just kind of summarize and then leave it off there, and let's see. Yes. So maybe we'll just state some theorems and then talk about why these theorems are true. So our theorem, the following are equivalent. So this is just a theorem kind of tying together all of these notions of linearly independent that we have. So we have a set of vectors. So given some collection of U1 up to UK, where each of these vectors, potentially in some n-dimensional space. So if we write a linear combination of the vectors and get 0, if this implies that all ti are equal to 0, it is the same as saying no vector in U is in the span of the others. And then it is also now the same as saying the equation AX equals 0. So think of this X x1 to xn, xk, excuse me, as our vector of coefficients or our vector of scalars, like that t1 to ti. You could call it t, but let's refrain from using capital T. Capital T. I think the book uses capital X. We can even use a lowercase x with a vector on it. Probably better. Capital T we'll use for linear transformations, which will start on Friday. So this equation only has the trivial solution. And we should specify what this matrix A is, where A is the matrix whose columns are formed by our set of vectors. So we've reduced our problem of linear independence. We can actually formulate that by looking at the matrix formed by whose columns are formed by the vectors in a given set. And we can either row reduce or perhaps LU factorize to determine if there's more solutions. The other thing we can do so let's let A be the matrix whose columns are formed by our set of vectors then the set is linearly independent if and only if A is invertible. So as we saw in that last example, what happened when we row reduced? Our coefficient matrix, we didn't get the identity. We didn't get ones along that diagonal, right? We had that row of zeros at the bottom, which ended up telling us that it was linearly dependent. So this we can essentially deduce from part 3 here, right? If we were to take a look at A inverse x equals 0, sorry. If we were to take a look at AX equals 0, so we're setting up this equation from number 3 of the previous theorem. Well, if A inverse exists, if it's invertible, this implies that we can multiply both sides of the equation by A inverse. A inverse. And so we will be left with x on the left, but a matrix acting on the 0 vector will always give us back the 0 vector. In other words, we arrive at the trivial solution again. So you can try to think along the other lines was if the trivial solution is the only one that exists, then how can we show A is invertible? That way is going to be a little bit harder. And then, so sorry for going over it. Let's write down one or maybe two more theorems, corollary. So suppose U is our collection of vectors, where each of the vectors are n-dimensional. If k is bigger than n, then U is not linearly independent. Namely, if I have more vectors than dimensions, we are not going to have a linearly independent set. This actually ties back into one of the exam problems where we wrote, if we have more equations than variables, is it possible to have a consistent solution? And so the answer to that is yes, it is. You kind of have redundant equations where you have extra equations whose solutions are still the same with only the two variables. And in some sense, that's going to correspond to the matrix of coefficients being created out of those. The rows are not linearly independent. And then let's see, I think we have one last theorem. So theorem. So for any vector v in the span of a set of vectors, then if that set of vectors is linearly independent, then we know that V is going to be written as some linear combination of those vectors, but it's unique. meaning there is only one solution. There is only one combination of these t's that when we multiply them by their corresponding u's and add them together, we will get v. We'll talk maybe a little bit more about this tomorrow. And then as well, tomorrow we will introduce the concept of bases. So highly related to this concept of linear independence. Any questions?